let us start looking at some circuits. So first we're going to define a few terms. Current is movement of charges, and by convention it is the movement of positive charges, even though we know that only negative charges are able to move. And the cause for this convention is Ben Franklin. He just had to pick one of the charges to be the one that moves in the circuit, and he accidentally picked the positive charges, and we've stuck with that. Now we know better. Back then they didn't know whether the protons or the electrons were moving in the circuit. The symbol for current is I, and current is delta Q over delta T, so the number of charges that are crossing a certain part of the wire in a certain amount of time. The units for current are the amperes or amps, and the symbol for them is just A. Another term is that of potential difference or voltage, and we've encountered that in an earlier video. So voltage can be produced by a battery or an electric generator. If it is a battery, then the type of current that it produces is direct current, so it only flows in one direction. If it is produced by an electric generator, that will become an alternating current because the direction changes with a certain frequency. Now, there is a special type of voltage, and that occurs when no charge is moving between the two terminals of the battery, and that voltage is called an electromotive force or an EMF. It is not a force, it is a voltage, even though the name may be misleading. So the units for this are also the volts. The units for voltage is just volts, and the symbol is V. Now, as I mentioned before, there are two types of currents, direct currents and alternating currents. Direct currents only flow in one direction, and alternating currents alternate direction. Another concept is that of a resistor. And resistors are little circuit elements that resist current flow. The symbol for the resistor is R, and they are measured in ohms, and the symbol for that is the capital omega. And in a circuit, a resistor looks like this. So then, if we want to complete a circuit, put a battery in there as well, then we'll close the circuit, and here we have the battery. Let's say that it has a certain EMF, electromotive force, and one important thing to know about the battery is that the longer terminal is positive, the shorter terminal is negative, and that means that the positive charges are going to go in this direction, and the current will be in this direction. Now, we can tell the direction of the current when there's only one loop in the circuit. It's going to get harder to figure out whether the current flows clockwise or counterclockwise through a loop when we have multiple loops. But for now, it is fairly clear that the current flows from a positive to the negative through the resistor. So from the higher potential to the lower potential. Now, the resistor is made out of a certain ceramic piece, and it looks like this. Oh, let's try again. Something like this. And there are various bands on here that tell you the value of the resistance. There's also leads coming out of it. So the resistor has a certain length, L. It has a certain cross-sectional area, A. So we can determine what the resistance of this is based on something we call resistivity. So the resistance is equal to the resistivity, that's the resistivity of the material that it's made of, times the length divided by the cross-sectional area A. So given a certain resistivity and the shape of a resistor, we can determine the resistance of this. Now, the resistivity of a resistor changes with temperature, so rho changes with temperature, and generally it increases. So with higher temperature, resistivity increases, which means that the resistance also increases. Now, one law that combines the terms that we discussed before is Ohm's law, and that says that the potential V is equal to the current times the resistance. So V equals IR. Another equation is that for power. So power is I times V, and if we substitute V as IR in this equation, we end up with power equals I squared R, or if we substitute the I from here, so that would be V over R, into there, then we end up with power being equal to V squared over R. Power is work over time, so the unit for power is the watt, and the symbol is W. Now, we can connect several resistors in a circuit, and let's say that we have 3 resistors in series. So I have R1, R2, R3. And there's a battery here. So here would be my EMF. Now, we know that the positive terminal is the longer one, the negative terminal is the shorter one, so we will have a current flowing through this circuit in this direction. Now, in series, the current is the same, so that means that the current through resistor R3 is I, the current through resistor R2 is I, and the current through resistor R1 is I as well. But there will be a different potential drop across each of the resistors. So this potential drop will be V3 equals I R3 by Ohm's law. The potential drop across R2 is going to be V2 equals I R2. And then the potential drop for R1 is going to be V1 equals I R1. But if we add potential drops V1 plus V2 plus V3, they have to add up to the EMF that the battery gave off, assuming that there is no energy loss in the system. So it is kind of a conservation of energy type concept here. So that means that if I add V1 to V2 and to V3, that will give me the EMF in the battery. So I'm going to substitute V1 with IR1, V2 with IR2, V3 with IR3, and the EMF is the current I that flows in series the same through all of the circuit elements times an equivalent resistance. So the battery doesn't really know how many resistors it sends a current through, but it does know that it encounters a resistance. And we call that resistance the equivalent resistance. So now if we divide everything by the current, we end up with the equivalent resistance in series being R1 plus R2 plus R3. So in series, resistors add as R1 plus R2 plus R3 plus and so on, as many resistors as we have. So here's the equation again. R equivalent is R1 plus R2 plus R3. Sorry, we went back. Then the current is the same in all series resistors. That's how we developed the equation. Then the voltage drop across each resistor is different, so we have to add those voltages to end up with voltage supplied by the battery. Now let us look at resistors in parallel. So in parallel, that's a capacitor. Let's try again. We have resistor 1, then parallel with that is resistor 2, parallel with that is resistor 3, and all of them are in are connected in parallel with a battery, with an EMF. So if we look at the terminals of resistor 3, so this one goes across the battery, then the terminals of R2 also go straight across the EMF, and the terminals of R1 go straight across the EMF, which means that all three resistors, R1, R2, and R3, have the same EMF across them. But the current will flow from plus, so in this direction. So the current will get to this junction, and it can go through R3, and then part of it can go through R3, and let's call this current I3. Then the rest of it will go in this direction. Some of it will go through R2, and we'll call that I2. And some of that will go through R1, and we'll call that I1. Well, the total current that the battery gave off has to add up to I1, I2, and I3 because, again, we assume that there is no loss of any type of energy in this circuit. So then we can say that I equals I1 plus I2 plus I3. And using Ohm's law, so in here, solving for I, we get V over R. So then the current given by the battery is the EMF divided by the equivalent resistance of the circuit, and that's equal to the EMF divided by R1 plus the EMF divided by R2 plus the EMF divided by R3. So dividing through by the EMF, we end up with 1 over R equivalent in parallel is 1 over R1 plus 1 over R2 plus 1 over R3. So that is how resistors add in parallel. The reason again is because in parallel the voltage is the same across all the resistors and the currents add up. So here's the equation again. The voltage drop is the same across all parallel resistors, and the current through parallel resistors is different, unless the resistors have the same value, of course. Kirchhoff's rules help to solve for various things in more complex circuits. So there are two rules. There's the junction rule that says that the sum of the currents that go into a junction has to equal the sum of the currents coming out of the junction. So again, it's kind of a conservation law. So let's say that we have a junction in which there are 3 wires joined. And if we have, let's say, current I1 going into this junction, current I2 going out of the junction, and let's say current I3 is also going out of the junction, then it makes sense that the amount of current that we put into this junction should be equal to the currents coming out of the junction. So in this situation, I1 has to be equal to I2 plus I3. So this is Kirchhoff's junction rule. The other rule is Kirchhoff's loop rule, and that says that the sum of the potential drops is equal to sum of the potential rises. That is a little bit more complicated to look at. So let's say that we have 2 resistors and a battery, and let's say that this is an EMF. So resistor 1, resistor 2. So the longer terminal is the positive one, the shorter is the negative one, which then means that a current will flow in this direction. So we have a current I, and the current, the potential in the branch from here all the way to there is the same. So we have the same potential here, but then as the current passes through R1, there will be a potential drop. So then we can label this side of the resistor as the positive, and then the potential will drop from plus to minus as it goes through the first resistor. Then In the next little branch here, the potential is going to be the same, but then it will drop again across the second resistor. So there will be another drop, plus minus, and then the current will just continue going back to the battery. So what Kirchhoff's loop rule says is that the sum of the potential rises, so going around the circuit in this direction, going from minus to plus across the battery would be a rise. We're going from a negative to a positive, so that's a potential rise, and that has to be equal to the potential drop across R1 and the potential drop across R2. So we'd say, I'll just write it under the equation, so sum of the potential drops, that would be just the EMF, equals sum of the potential rises, which is I R1 plus I R2. In a next video, we will look at a more complex example for Kirchhoff's rules.